guys, my name is Courtney. I'm a fifth-year PhD student in the Department of Chemistry. I work in the research group of Professor Michael Nippe. I'm originally from Calgary, Canada. I came to Texas A&M in 2013. So in our group, we work on making really small magnets. And so these are single molecules or discrete molecules that have the same properties as bulk magnets, including magnetic hysteresis or magnetic memory. And so these could potentially be utilized in high-density data storage as well as in quantum computing. So molecules can have like a spin up or a spin down. Right now, in data storage, information is stored as bits, so a 1 or a 0. You could imagine storing like a 1 being a spin up or a 0 being a spin down, and then you could store data in the form of molecular spin. Alright, so most of my work is extremely air sensitive, and so I have to do all my work under inert gases like nitrogen and argon. And so I like to spend most of my day in the glove box. So this is one of our glove boxes here.
Typical day.
Let's turn the light on. So the glove box is filled with argon. And so I do a lot of my chemistry in here just to keep it oxygen and water free.
Cool.
To bring anything in and out of the box, we have to put it in these antechambers under vacuum for several hours. So it requires a lot of planning to do an experiment to make sure that you have everything you need inside of the glove box.
Nice. And you have to wear those ski goggles all the time?
Yeah, safety first. Alright, cool. So to use the glove box, make sure first that not wearing any jewelry or anything that can puncture the gloves. And then, since the glove box is attached to a vacuum, if you put your arms in, it automatically removes the excess pressure. And then once inside the box, you can just work like normal. You don't have much dexterity, so it is a little bit hard to grab really tiny things. We also have dry solvents that come into the box here, so it's really important that everything is kept very water-free and air-free.
So what specifically do you work on for developing the magnets?
So I work with the lanthanides, which I like to call the basement of the periodic table, because it's really the part that nobody thinks about. I mainly work with dysprosium. Because of the really high single ion anisotropy, makes for really good single molecule magnets. So sometimes I can't do all of my chemistry in the glove box, especially if it involves like heating something. So what we use outside of the box is called a Schlenk line. And so what we have here is a Schlenk line. So the bottom manifold is vacuum, and there's two nitrogen manifolds. And so we use this to evacuate flasks and refill it with inert gas like nitrogen. We can also use this to remove solvents. This is all custom made.
Nice.
Yes. We have a glass blower in the chemistry department, and he can make really awesome things. So he made all of our Schlenk lines. Yeah.
Wow. Alright, so we're now in the squid with Courtney, and she's going to tell us about what this loud machine does.
Right, so this is a squid magnetometer. The squid stands for superconducting quantum interference device. This is where I do all the magnetic measurements on the materials that I make. We can go as low as temperatures to as low as 1.8 Kelvin on this instrument. And so how we do that is we have helium gas attached. The helium gas is condensed inside the squid to make liquid helium, which lets us achieve very low temperatures for our measurements. We can also go up to fields as high as 7 Tesla to measure the materials. So the sample is loaded very far down in the instrument. So what we do is we load the sample on this long sample rod here. And we actually load it in a drinking straw. Our sample, so it's a $500,000 instrument, but we load our samples in drinking straws. We affix them onto the sample rod and we put them in the instrument. Surprisingly, drinking straws stay together at 1.8 Kelvin, so that's something that I wouldn't have expected at first. Yeah, I use this on a weekly basis. Cool. We also do dynamic magnetic measurements, so for those what we do is we apply an alternating field at a certain frequency, so the field is moving like up, down at a certain frequency. And then at some point when the frequency becomes fast enough, the molecule cannot relax, the magnetic moment cannot relax fast enough to keep up with the field, and so what we get is some of the moment is then out of phase with the alternating field, and we see a signal which can indicate that there's slow relaxation. Slow relaxation is what we're looking for because we're interested in materials that can retain magnetic properties or retain magnetic memory.
Cool. Cool. So what do you want to do? What do you think you want to do when you're done with grad school?
So I'm almost done with grad school. I'll be defending around May, and I'm hoping to go into industry and working on R&D.